Hey everyone, welcome back to the channel Code with AKJ. Today is day 46 of solving LeetCode 75 challenge. And today's problem is evaluate division from graph DFS. And this is the last question from graph DFS section. So we'll start with a brute force approach and then we'll optimize it step by step. And by the end of this video, you'll have a solid understanding of both graph traversal and efficient query evaluation. So if you're new here, don't forget to subscribe and hit that bell icon so you never miss any daily coding videos. So let's get started. So the problem statement says you are given an array of variable pairs, equations and an array of real numbers values where equations of I is equals to A of I, comma B of I and values of I represent the equation AI slash BI. So each AI or BI is a string that represents a single variable. You are also given some queries where queries of J is CJ and DJ represents the jth query where you must find the answer for CJ slash DJ. So we need to return all the answers to all the queries. If a single answer cannot be determined, return -1.0. We have given two notes here. The input is always valid. You may assume that evaluating the queries will not result in division by 0 and there is no contradiction. And the variables that do not occur in the list of equations are undefined, so the answer cannot be determined for them. So let's understand this given problem statement with the help of these examples. So let's look at example 1. We have given equations A, B, B, C and their values 2.0 and 3.0. And the queries here are AC, BA, AE, AA and XX. Variables A, B and BC. And the values here are 2.0 and 3.0 respectively, which means the A by B is 2.0 and B by C is 3.0. And the queries which we need to evaluate are AC, that means A by C, B by A by E, A by A and X by X. Given here are the values A by B is 2.0 and B by C is 3.0 and we need to find A by C. So to find A by C we need to evaluate these equations first. By looking at these two equations we can see that to find out A by C we need to multiply these two equations, that is A by B into B by C, where B gets cancelled and we'll get A by C as 2.0 into 3.0, which will give us 6.0. So in the same way we need to calculate B by A with the help of these two equations, and in the same way we need to find A by E, A by A and X and X. Here we need to check that E is not present in our equations, that is A, B, C. So we have three variables here in our equations. And since E is not present in our equations, we'll directly return -1. In the same way, X and X, where X are not present in our equations, so we'll directly return -1 in that case as well. So finally the output for our first example would be 6, 0.5, -1, 1 and -1. So in the same way, let's look at our example 2. Here we have given equations A by B as 1.5, B by C as 2.5 and BC by CD as 5.0. And the queries which we need to evaluate are A by C by B and BC by CD and CD by BC. So while calculating these, we'll get our answers as 3.75, 0.4, 5 and 0.2. So this was the problem statement where we have given equations, that is A by B, so with their values in the values vector, and we are also given few queries which we need to evaluate based on our equations and their values. So let's try to solve this problem. After carefully observing these equations and values, we can consider this as a graph problem where each and every variable is considered as a node and each equation is an edge with weight. For example, A by B gives us 2.0. So here A and B are considered as node and the distance between A and B has a weight 2.0. So in this way, we'll consider this whole problem as a graph problem where we'll consider each and every variable here as a node and the values here are the weight between these two nodes. So for this given graph problem, we have three nodes A, B and C and the weights between them are 2.0 and 3.0. And since the queries here are from B to A as well, from this we can also observe that this graph is an undirected graph. So we need to make sure that while creating a graph with the help of these equations, we should have an edge from A to B and B to A as well. So while creating those edges, we need to make sure that, for example, from A to B, we have a value 2. And for B to A, we will make these values as 1 by values of I. And with the help of that particular graph, we'll try to evaluate all these particular queries by using a DFS function which will find a path from numerator to the denominator. So we'll consider each and every variable in these queries of I as a source node and a destination node, and we'll use a DFS function to find a path from this source node to destination node, and while finding this path, we'll also calculate the total weight, and the total weight we have calculated from source to destination, and finally after reaching our destination point, we'll return that total weight. So that would be our answer for that particular query from source to destination. So let's quickly understand how our approach works with the help of this given example 1, and later on we'll move on to the code with its time and space complexity. So here I have represented the example 1 in the form of graph where each and every variable is considered as a node, and the value of I is considered as the weight between these two variables. So from A to B we have a weight 2, and since it is an undirected graph, there's a reverse edge from B to A as well, and the value is also reverse, which is 1 by 2. So from B to C the value was 3, and the reverse edge from C to B would have the reverse value, that is 1 by 3. And for this given graph we have created an adjacency list which is of type string to vector of pair of string comma int. So since all these variables are in the form of string, our key value would be in the form of string, and the value here would be in the form of pair of string comma int. So let's quickly understand how our approach works here. So first step here would be to create a graph out of equations and values vector. So this was our first step, that is creating a graph from our equations and values of vector. And the step 2 here would be to evaluate our queries. We are also given queries vector where each queries of I contains a source and destination node. Grab the source node and destination node. So after grabbing this source and destination node, we'll first check whether two nodes are present in a graph or not. So if it is present, we'll carry on with our next step, and if it is not present, we can directly return -1 as we don't have these nodes in our graph. We'll also check if the source node is equals to the destination node or not, which means if any of the query has A comma A or B comma B or C comma C, we can directly return the value as 1.0 as A by A or B by B or C by B gives us value 1. So this would be our another check, that if source node or destination node, they both are equal or not. So if they are equal, we'll return 1.0. Inside our second step, we'll have two sub steps, that is if any of the source node or destination node is not present in our graph, then we'll return -1, or if the source node and destination node are same, then we'll return 1.0. We'll continue with our evaluation of our query. So let's do a quick try run on one of our query. So we'll just take a query A comma C. So we'll grab the U value or V value, that is the source node here is A and the destination node here is C. So with the help of a DFS function, we'll try to find a path between the source to destination, and while reaching from source to destination, we'll calculate our value. And after reaching our destination node, we'll return this value as an answer. So we'll have a DFS function which will give us that particular value, and to track whether we have visited a particular node in our graph or not, so we'll take a set which would store all the nodes which have been visited so that we don't visit the same node again. So let's understand how this DFS function works, and let's do a quick dry run on this given query A comma C. So DFS function starts making the current node as visited. So we'll first start with our source node, that to insert this node inside our set, which means we have visited this node currently. So the first step here would be to mark current node as true by inserting it in set. And second step here would be to go through the current node's neighbor and check whether it is visited or not. So the current node is A and its neighbor is B with its value 2. So after grabbing these two values, B and 2, so in our DFS function, we will also be sending a value, initial value, which would be 1.0. So while calculating and reaching the destination node, this value would be multiplied with the neighbor's weight. So while grabbing the current node weight, we'll also calculate the total value. So after grabbing these two variables, we'll first check whether this given neighbor is already visited or not with the help of our set. So here we can see that in our set we don't have a node B. So since it is not visited, we'll again give a DFS function and calculate our total value. The given neighbor is not visited, we'll again call a DFS function calculating our weight. So here initial value was 1.0 and here the weight is 2, which gives us 2.0. So again this DFS function goes through the neighbors of B. So here we have two neighbors for B, one is A and one is C. A is already inside our set, which means it is already being visited. We'll ignore this. So again the next neighbor here is C. So since C is not visited, we'll again give a DFS function and sending C as a current node, and we'll calculate its value with the help of its weight. So the weight here is 3 and last calculated value was 2.0 with the current value 3, which gives us 6.0. So the current weight here is 6.0 and the current node is C. So for every DFS function we'll be having a base function. So here in our case this DFS function will have a base function called if the current node is equals to the target node. It means we have reached our destination node. So in this case we'll store the value inside our result variable. So we'll also send a result variable inside our DFS function. So we'll store that total calculated value inside our result variable and we'll return from our function. So this would be our base case and this would be our steps for our approach. So let's quickly draw the DFS function tree to understand how these calls get called. So initially we'll start from our source node. So initially we'll start from our source node, sending the initial value as 1.0. We'll also send the destination value. We'll also send the initial result variable, the set. So since the source node here is A, our first step here would be to store it inside our set, and we'll go through all its neighbors. So the neighbor of A is B from our adjacency list. So we'll give a DFS function call to B. So sending B destination result variable set, and the updated value would be 1.0 into 2. So here the value would be 2. So again from B we have two neighbors. So we'll give two DFS calls, DFS to A again, going back with value 2.0. But since A is already being visited, we'll neglect this DFS call. We'll also have a DFS call to C with the destination node, result and set with our updated weight, which is 6.0. So here since the current node is C and the destination node is also C, since they both match, store the value which is 6.0 in our result variable and will return from our function. So it will give as true. So our DFS function return type would be in the form of bool. So this function call gives us true as we have reached our destination function. So it returns true. Again from this call it returns true, and from this call it returns true. So our DFS function gets completed and our result variable contains value 6.0. So for this given query A comma C, our answer would be 6.0. So in the same way, let's take few more queries. So for example, we have query B to A. So here the source node is B and destination node is A. We'll again give a DFS call from B, sending initial value as 1.0. Since for B we have two neighbors, that is A and C, we'll calculate its values. So the neighbor is A with a value 1 by 2. So the overall value would be 1.0 into 1.2, which would give us 0.5. This DFS call will never make us reach the destination node, which is A. So we'll neglect these calls, and since we have found our destination node, we'll return this current value. We'll store it in a result variable, which is 0.5. And since we have reached our destination node, which will return true for this function call, we'll stop our DFS function and we'll return the result variable as an answer, which is 0.500 in this case. If we consider a few more queries like A to A or B to B or C to C. We have these checks in our initial steps while evaluating the queries. So we'll directly return 1.0 in this case. And for the queries like A to X or X to X, since X is not present in our graph, we'll again return -1 in this case. So I think I considered all the cases and the edge cases for this given problem statement. So this was the approach. So let's quickly go through the time and space complexity and then we'll code this given problem. So the time complexity of this approach would be, so since we are building up a graph using the equations and values array, so each equations add two edges, that is bidirectional. So O of E would be one of the time complexity for building the graph. And again, for each query, in the worst case, we are using a DFS function which would visit all the V nodes, where V is the number of unique variables, and all the E edges if the graph is connected and the destination is far, that is in our case A to C. So our Q queries, our worst case total time would be O of Q cross V plus E. So this would be for the queries, and this is for building the graph. So the total time complexity in our case here would be O of E plus Q star V plus E. So for our approach, the time complexity would be O of E plus Q star V plus E. And coming to the space complexity, we are storing the graph using an adjacency list, where we are using unordered map of string, comma, vector of pair of string, comma, double. So it stores two directed edges for each equation. So the space complexity would be O of E for that. And secondly, we are using visited set for DFS, which may contain V variables during each query. So for that, we'll have O of V space complexity. And because of using DFS, we'll have a recursive calls. So for that, we have O of V. So the total space complexity for this approach would be O of V plus E. So this was a detailed time and space complexity of our approach. So let's quickly code our approach and submit. So let's quickly code our approach. So initially, I'll declare our adjacency list globally so that we can access in any of our functions. So our adjacency list would be in the form of string, comma, vector of pair of string, comma, double. So our first step here would be to build a graph with the help of our equations and values vector. So we'll use a for loop. We'll iterate over our equations vector. We'll grab both the values, that is u, which would be equations of I of 0, and v, which would be equations of I of 1. I will try to connect them in both the directions. So adjacency of u, push back, since it would store the pair of string, comma, double. In the same way, since it is bidirectional, adjacency of v would be connected back with u, but with reversed value, that is 1.0 by values of I. This way we have built our graph with the help of our equations and values vector. Our second step here would be to evaluate our queries. So we need to return the vector of double. We'll first declare our result vector, which would be of type double. We'll go through our queries with the help of for each loop. We'll grab our source node, which would be stored in x of o, and destination node, which would be stored in x of 1. So we'll have two sub steps here before moving on to our DFS function. Our first sub step is to check whether this given source and destination node is present in our adjacency list or not. So if adjacency dot count of src or not of adjacency dot count of destination. Count is an inbuilt function present in C++, which would help us find whether this given node is present in our adjacency or not. So if any of them is not present in our adjacency list, we'll push the value -1 inside our result vector, and we'll continue with our next step. So this was our first check, and another check here would be that if the source node is equals to the destination node. So if it is, we'll push back 1.0 inside our result vector and continue with our next step. So after doing these two checks, our third step here would be to first create our set, which would be of string type, and we'll name it as visited. We'll also take a double res variable, which would be storing 1.0 initially. And now we'll call our DFS function, where we will be sending our source node, destination node, visited set, result variable, and our initial value, which is 1.0. And after this given DFS function, we'll get our value and we'll store that value inside our result vector. So for every query, we'll grab the source and destination node and we'll first check whether it is present in our graph or not. So if it is not present, we'll push -1 inside our result vector and we'll move on to the next query. And we'll do a second check whether if source and destination, they both are equal. So if they both are equal, we'll push 1 inside our result vector and we'll move on to the next query. So if not, we'll use our visited set and we'll call our DFS function, send source and destination node along with our result variable and initial value, which is 1.0. So this whole operation would be done for each and every query inside our queries vector. So after finishing our queries vector and evaluating each and every query, we'll return our result vector. This result vector would store all the evaluated queries. So let's quickly code our DFS function and submit. So the return type of our DFS function would be either true or false. So it would be bool. Takes current node, which is the starting node. It also takes the destination node and it takes the visited set. We'll send it by reference. DFS function also takes the result variable. So since we need that result variable, we'll also send this by reference. And finally, a double value, which would be initially 1.2. So our base case here would be if the current node is equals to the destination node, which means we have reached our destination node. Then we'll store the value inside our result variable and we'll return. So this was our base case. And in our DFS function, our first step here would be to insert the current node inside our set, which means we have marked the current node as visited. And then go through its neighbor, iterate over the adjacency values or the neighbor values of the current node. So here adjacency list is being accessed as we have declared the adjacency list globally. And now we'll first check whether the neighbor is already visited in our set or not. So whether this particular neighbor is already being visited or not. So if it is not visited, we'll again give a DFS call, sending the neighbor, the destination node, the visited set, the result variable, calculated value. So here the calculated value would be value into weight. And if this given DFS function returns true, which means we have found our destination node, we have reached the destination node with the help of this neighbor, then we'll return true. And if we have not reached the destination node, we'll return false. So this was the code for our approach. So the time complexity for this approach was O of E plus Q cross V plus E. So O of E for building the graph, and for every query Q, we are again calling a DFS function which takes O of V plus E time complexity. So the overall time complexity is O of E plus O of Q cross V plus E. Whereas the space complexity here is, since we are using adjacency list which stores each and every edge, so O of E. And again for the recursive call O of V, so the overall space complexity here would be O of V plus E. So let's quickly run this code. It's working, so let's submit. As you can see, this gives a successful submission. So since the number of equations and queries were small, particular approach got successfully submitted. But if our equations and queries were more than a certain limit, then this approach would give us time limit exceeded. So in that case, we'll be using memorization method, where we'll be storing each and every current state's value inside a separate vector, which would take another space. And then we'll be able to handle the queries which are more than 20 here. So suppose the query's length here is only 20, so this particular approach got submitted. But if the query's length would be more than 20 or more than 100, then this would probably give us time limit exceeded. So in that case, we'll memoize this method. And if the value which is very, very large value, then we'll be using another optimized approach, which would be Floyd Warshall's algorithm. So with the help of that particular algorithm, we'll easily calculate the values of each and every edge, and then we'll finally look up that particular value in O of 1 time complexity. So that would be the optimized approach for this given problem statement. But since the time constraints here are very less, this approach is fast enough. So this is all about our problem, evaluate division. So this problem teaches us how equations can be modeled as graphs with weights, and it tests your understanding of DFS graph construction and query evaluation. So if this video helped you understand the problem better, don't forget to like, comment and share. And also subscribe for more such well-explained coding problems. I'll see you in the next video, which is day 47 of LeetCode 75 challenge. So until then, keep learning, keep coding. Thank you.